Welcome to day 7 of the macOS and iOS Security Internals Advent Calendar. Today we will be looking at kernel boot arguments. So what are kernel boot arguments? Basically the idea is that when a kernel boots, it is possible to pass arguments to it, the so-called kernel boot arguments. These arguments exist in wide variety and control various different features inside the kernel. They're usually undocumented. Well, maybe they are slightly documented in the source code, but aside from that, there exists a bunch of them that are not really fully documented at all. The main kernel checks these boot arguments mostly, but also drivers, more and more drivers are actually using kernel boot arguments to control some of their features. And even these days, some of these boot arguments are evaluated from userland. So various daemons or userland tools might check if certain kernel boot arguments are set, and then they behave accordingly. So here is a small subset of possible kernel boot arguments that exists. You have the -v, which activates a verbose boot. It's especially very popular among jailbreakers who like to see their iOS device booting in a verbose mode. Then you have the debug kernel boot argument, which is mostly for controlling debugging features like the kernel debugger. And then we have a few debugging features of the zone heap inside the kernel, which is -zc, zrex, and zlog. Those activate certain different kinds of logging features inside the kernel heap itself. So now the remainder here on the slide deck are all security relevant kernel boot arguments. And nowadays they are all protected by ifdefs. So nowadays you will only find them in debug and development kernels. That was not always the case. The purpose of these boot arguments is basically to disable certain kernel security features at boot time already. So if you have a debugging kernel, you can basically disable a bunch of security features from the kernel boot args themselves. For example, here you have the data const row, which basically disables the read-only protection of the kernel data const segment. You have unsafe kernel tags, which disables the PPL policies checks. You have disable ASLR, which allows you to disable userland ASLR. WP kernel is the write protection of the kernel, but that's an x86-64 specific kernel boot argument, where unsafe kernel text was basically ARM64 specific. So how do you get the boot arguments? In kernel land, they basically usually get retrieved via a certain function that is called pe_pass_boot_argn. The prototype of the function you can see here on the slide, and yes, that is one of the main ways how the kernel or kernel drivers use kernel boot arguments. Then for a while now, the kernel defines so-called tunables. These are basically kernel, usually read-only variables that control certain kernel features, and they can be modified from the kernel boot argument. And so for that we have the tunable macro that basically defines a certain boot argument and a variable that is then controlled by the boot argument. For example, here you see that the kernel boot argument debug is nowadays implemented as a tunable, so it controls the value of the debug boot arg variable, and the default value here is basically 0 if no boot argument is given. So that was the kernel level. In user space, tools also retrieve the kernel boot arguments, and what they usually do is they ask the sysctl interface directly with something like sysctl by name for the kern.bootargs sysctl entry. You can also do this on the command line with sysctl kern.bootargs, and it will then spit out the current kernel boot arguments as a sysctl string. Here you can see that debug equals 1 and verbose mode is activated. This is, however, a little bit tricky because the return string is truncated at 256 bytes. So if the kernel boot arguments are actually longer than that, they will actually get truncated here. There's daemons like the kex daemon in the past, but also launchd, the command line tool, not the command line tool, the basically the launch daemon process that basically control the security of the system via the kernel boot args. So they check if certain features are activated or deactivated, and then they relax their own security. So how do you, as the security researcher, or in any case the end user, set your own kernel boot arguments? There are basically two possible ways. One is to modify the entry in the NVRAM, but we know since the SIP chapter that we can only set NVRAM variables if SIP is deactivated. Actually, that's not a complete truth. The reality is that when you set an NVRAM variable, you trigger a certain sandbox profile entry, and there are certain whitelisted boot arguments that are not problematic, like for example the -v, the verbose boot, that are allowed to be set even when SIP is activated. But normally everything that is sensitive would not be allowed by SIP. So you first have to disable SIP like we did before to be able to set arbitrary boot arguments. There's an alternative way to set kernel boot arguments that does not involve the NVRAM, and that's basically writing a certain file that is library preferences system configuration com.apple.boot.plist, and there's an entry called kernel flags, and when you modify this you basically also modify the kernel boot arguments, and when the system reboots, the NVRAM entry and this file entry will be merged together, so together they form the actual used kernel boot arguments. This file, however, is also protected by SIP, so again, if you want to modify this file, you actually need to be able to disable SIP first. So here's an example how you do this NVRAM programming. On the command line, you just do sudo NVRAM, and here you say bootargs equals, and here's wp kernel equals 0 and -v, which would normally disable the write protection of the kernel. But again, I told you before that nowadays this is only a valid boot argument on development or debugging kernel. And here, for completeness, the file that you can edit, it's an plist file, and as you can see here, the XML, there is already a kernel flex in here with a -v, which means the kernel boot argument for verbose booting is selected here. Yeah, here you could modify this and save it, and then on the next boot you would have the specific kernel boot arguments being used. So, and now we can go and have a look into how drivers and userland daemons make use of kernel boot arguments. For that, we will use our favorite tool, IDA, and just have a look into the specific drivers and userland tools. Okay, now let's have a look into what boot arguments are used by kernel drivers. For that, we need to remember that all these drivers on macOS are in system library extensions, Of course, there's also library extension, but let's say the normal drivers. And as you can see, there's quite a few of these drivers here. So now let's see which of those actually make use of kernel boot args. So for that we use grep, we do it recursively, and we search for the string pe_parse boot arg, and we go to system library extensions and see what drivers are actually matching here. And when you do this, you can see, oh, there's actually quite a lot of drivers that are matching this, which means we have a lot to potentially look at. When we look here, we see, for example, there's the sandbox extension, there's the core crypto extension, there's something called trusted accessory, the tree star ship, and yeah, I think the easiest thing is that we just look into sandbox and maybe core crypto and see what they're actually doing there. So to make it easier for IDA, we just copy these files to here. So first this and also this one here. And now I will open them inside IDA. So here we have the sandbox driver, and now we can look for the pe_parse boot argn. We have the function here once. We are looking for the cross references, and we have here something in the policy init. Let's decode this. So apparently there's a sandbox serial reporting. So apparently it does some reporting to the serial in case of sandbox events. Yeah, that's basically it. So obviously this is completely undocumented, and so let's see what other undocumented stuff is maybe in core crypto. So now let's look at core crypto. So we have core crypto here. Let's again search for boot args. We do the cross reference again. So it's apparently again here something. So it obviously has a fips_mode thing. And yeah, the FIPS mode can be set via a boot argument. And that's then passed to this FIPS post function here, which does some FIPS stuff apparently. What this does exactly, no idea. This would require more reversing to see what's going on here. But that's not the point of this exercise. The point of this exercise is to actually see how do we find undocumented kernel boot arguments that might give us help for certain debugging. Okay, so this was in the drivers. Now let's have a look at userland daemons and processes. For that we can do grep again, but this time we do kern.bootargs and we look for example /sbin, and we try to redirect all errors to def null. So we see that in sbin only launch D matches, and let's see user sbin. There's a few more, and let's look in user libexec. So there is apparently also a number of things that have kernel boot arguments. Yeah, so let's have a look into the launch D first, and then maybe watchdog D. That should be enough. So let's copy sbin launch D here and copy the user libexec watchdog here. And again, let's open this in IDA. So launch D is first. So this time we have to look for the strings. So we go to view, subviews, strings. We look for the boot args, current boot args here. Let's have a look. There's actually two cross references here. Let's have a look. So we have a function here, current boot arg. So let's see what this is doing. So it's basically a sysctl by name wrapper. So that means this here reads the current boot args. It prints out the boot args here, and that was already it actually here. Then let's see the other usage of boot args. So here again, this is our sysctl by name wrapper. This is our boot args. And v0 is okay. Let's see. Let's call this the boot arg. So we have here a check for -v. Here we seems to have a check for -no corpse. Here we have server perf mode equals 1, rc.trampoline equals something, launch the instance limit, launch the user abandon unmanaged, launch the verbose correlation logs. That's basically it. So all of these are kernel boot arguments that actually control launch D. Okay, so now let's have a look at watchdog D. And when we look into this and look for the strings again, no, that was not correct apparently. Oh wait, this needs to be go over here, and we look for boot arg. Kernel boot args gets called from here. Let's have a look. So here we have sysctl by name. It's writing the boot argument in here. Okay. Let's name this the global boot arg. And let's see where this is read. So there's apparently another function that accesses it. No, wait. Here's the other function that accesses it. So apparently this function here, when called, returns the global boot arg. Let's see where this is called. Let's call this get global boot arg. So it's called here. So here apparently it checks for wdt underscore test, wdt controller, wdt ephemeral, yeah, controller wt, wt no pmu. So here it's apparently also readings from somewhere else, from the device tree, instead of the kernel boot arguments. So that's a different way to get the boot arguments basically. Here you see again it tests wt test healthy, tm no panic, tm panic. So there's a bunch of this stuff that it's actually checking for. And let's have a look. We have other function that makes use of it. Here, apparently it checks for wdt no pmu. Here, disable coproc, rsdwt, and so on, the panic immediately, and wt logging. So obviously there's quite a few wdt kernel boot arguments. Of course, again, all of them are completely undocumented, and if they have any usage for you as a security researcher, it's completely up to you to find that out. And some of them might be interesting, some others might be just not for you, or just for different kinds of debugging, like for people who write actual code.